Hello everybody. In this video we are going to begin talking about local rings. So a ring is called a local ring if it has a unique maximal ideal. Or an equivalent way to say it is a ring is called a local ring if the Jacobson radical, remember the Jacobson radical is the intersection of all maximal ideals, if this Jacobson radical is itself a maximal ideal.
So let's state the first lemma. We have the following. R is a local ring if and only if every element of R minus M, so every element in the complement of the maximal ideal M, is a unit. So is an element in the ring that can be inverted. Proof. Let's first assume that R is a local ring. With unique maximal ideal M. And then we want to show the implication that every element of the complement, so every element in R minus M, is a unit. So assume that A in R is not a unit. Then we can look at the ideal generated by this element A, which I denote in these pointed brackets. So this is the ideal generated by A. And this, of course, is contained in a maximal ideal, since every ideal is contained in a maximal ideal by Zorn's lemma. So, since by assumption there is only one maximal ideal, we have that this ideal generated by A is in M. And this, of course, implies that A is an element of M, because the ideal generated by A is in M, so in particular A has to be in M. And this, of course, proves this direction, since what we are saying is if an element is not a unit, it is in M. So if it is in the complement, it has to be a unit. So this concludes the first part of the proof. Now let's look at the other direction. So in the other direction, we assume that every element of the complement of M is a unit. And we want to show that this ring R has a unique maximal ideal. So in other words, we want to show that every ideal I, which is of course a proper ideal, has to be contained in M. And that's fairly easy to see because a proper ideal, of course, cannot contain a unit, because if it would contain a unit, it would contain 1, and thus it would be R, which is certainly not a proper ideal. So what we are saying here is that such a proper ideal cannot contain an element of the complement of M. So this ideal I, which is a proper ideal, has to be in M. And yeah, this shows every proper ideal is contained in M, so M is the unique maximal ideal. And this is our second part of the proof. And yeah, that's basically it for this lemma. So in the next mini lecture, we are going to show yet another condition for a local ring that is equivalent. So for now, thank you for watching and see you next time.